Welcome to the second in our series of flow chemistry webinars. Today we're going to be talking about some of the key benefits of flow chemistry and why you might want to perform your chemistry in continuous flow. So brief introduction, my name's Andrew Mansfield. I'm in charge of flow chemistry products at Syrris. My background is as an organic chemist. I spent most of my career in the pharma industry, where I've implemented flow chemistry. I've also worked in academia, and also now in the commercial zone. So if you attended the first session, we spoke about what flow chemistry is and discussed the principles behind flow chemistry. We're going to go into a little bit more detail with the time that we have and talk about some of the key benefits. So I just want to start off by introducing the company. I'll be very brief. I work for Syrris, the chemistry arm of a company called Black Trace. Now, the whole of Black Trace, and you can see the number of different brands that we have for different applications on the bottom of this slide, is all generated from flow chemistry. Syrris as a company started with collaborations to look at flow chemistry or microfluidics with a chemistry slant all the way back in 2001. And as a company, we produced the first commercial flow chemistry system all the way back in 2003. So we have lots of experience in-house on running flow chemistry experiments and developing flow chemistry apparatus. So if you have any questions, please get in contact with us. If you've got any questions about anything that we talk about here today, please use the chat function in the webinar software, and we'll try and answer those questions at the end of the session. If I don't have time, I will get back and answer every question that's asked. So this is the agenda for today. For those that didn't attend the first webinar, I'll just have a brief recap on what flow chemistry is. I'll talk about some of the key benefits, and then we'll run through some chemistry examples just to illustrate those points. And at the end, as I say, we'll have a question and answer session. So we run lots of workshops as an introduction to flow chemistry globally, and it's always nice to understand people's experience when we start these off. So I'm just going to put a quick poll up just to work out what level of exposure you've had to flow chemistry, whether you use the technique at all in your institute or company. So if you just spend a moment just to fill the poll in. I have an assistant off screen who's just compiling those results. So just bear with me. It doesn't matter if you have no experience or no knowledge of flow chemistry. These workshops, these webinars are designed to bring everyone up to a level of understanding of what flow chemistry is and what it can offer. Future webinars will be talking about converting your batch chemistry to a continuous process and talk about some more in-depth applications. So, okay, that's as I'd expect. Most people are on the beginnings of their flow chemistry journey, so to speak. That's okay, we'll bring everyone up to the same level and continue the webinars on as the series expands. So let's have a brief recap on what flow chemistry is. So I always start off by saying flow chemistry is a synthetic technique. It's just another tool in our toolbox as chemists to enable us to perform our chemistry better. Now, I emphasize on that, it's just a tool, but it's a tool that allows us to increase the control of our reaction parameters. If we can control our key reaction parameters, we can often get better selectivity, high yielding reactions, less byproducts, less waste, etc. And the type of parameters we're thinking about are things like reaction temperature, mixing and addition, reaction times, stoichiometric ratio, and molar ratio control. If we can control our key reaction parameters in more detail, then we can generally have a wider range of control for a broad range of chemistry applications. Okay, so what is flow chemistry? In its simplest description, flow chemistry is a process where our reagents are continuously pumped through a flow reactor and the products continuously collected. So I've got a little cartoon here just to illustrate that. So we've got a simple system. We have reagent A and B. We have a reaction here where we've got two inputs. If we know the concentration of our reagents, by simply varying the speed, the flow rate that we introduce those reagents into our flowing stream, we can control the molar ratio extremely precisely. So we can get selectivity there. So we need to mix our reagents. If we flow our reagents into the flowing stream, they will mix at some point, whether this is a T mixer or a simple static mixer for reactions where we need faster mass transfer. So we mix and then we pass our reagents through a temperature controlled reactor and we continuously elute them. So this is where the continuous and the flow in this process comes from. We're continuously pumping our reagents, they're continuously reacting, and they're continuously eluting. So to understand some of the benefits, we need to understand how we carry out chemistry that's familiar with us. So batch chemistry is a classical way of carrying out chemical reactions. It's something that we're all familiar with. It's a technique that's been used for hundreds of years. So we all know how to do this. We take our reagents, we load them into a reactor, we heat and stir them for a period of time. When our reaction's complete, we need to take those out of the vessel, work them up in some way and isolate our compounds. So the key kind of parameters we're thinking about are things like mixing and addition, reaction temperature, reaction time, concentrations, those kinds of things that are familiar to us. In a flow chemistry experiment, as we've said, we're continuously pumping our reagents and we're continuously reacting and eluting them. But we're still thinking about those reaction parameters, the same reaction conditions that we would use under batch conditions. So those being mixing and addition, reaction temperature, reaction time. But now in flow chemistry, we're calling that residence time. That's the time that every portion of our reaction spends in that reactive environment. And we can also add a third component, a fourth component to that equation. That's pressure. It's very easy to pressurize flow chemistry systems, and that can give us lots of benefits. So I guess what we're here for is to talk about why you would use a new synthetic technique over one that you're familiar with. So there are some key benefits that I'm going to highlight here, and we'll go through those in more detail as we progress this up and today. So we can potentially increase reaction rates. We can run faster reactions if our reactions are thermodynamically controlled. We can potentially run safer reactions. We can reduce the associated hazards with certain chemistry. We can perform reaction optimization in a faster and more efficient process by means of automation. This is a big statement, we can possibly achieve reactions or reaction conditions that aren't possible under traditional methods. So we can create things like reactive intermediates in situ and react them all. We can create hazardous reagents and use them continuously. We can use the benefits or the technology of flow chemistry to make library arrays of compounds, and we can easily explore the diverse chemical space, harnessing the benefits. Our reactions are generally more selective. If we can increase the control of our reaction parameters, then generally we can be more selective in our reaction pathways. Scale up is easier in flow rather than batch. We can scale up from milligrams to kilograms with very little effort and resynthesis. Not only can we create and perform our reaction continuously, but we can also apply technology to do inline workup as well. So we can work up our reaction continuously. And we can integrate things like reaction analysis to continuously monitor the progression of our reaction, to get real-time feedback of our reaction progression. So let's think about some of the benefits. So the first one here would be selectivity. So let's think about running our reactions in batch. So step back a second. Poor selectivity generally comes from loss of reaction control or some variation in our reaction conditions. And we're thinking about parameters such as temperature, mixing, addition, molar ratios, concentration, time, things that we mentioned before. So if we think about the first one, temperature, when we're running our reaction in a batch reactor, whatever that is, a round bottom flask or a jacketed reactor, or simply a small vial. When we're heating from the outside in. Our reaction will become homogeneous in temperature over time, but we generate a temperature gradient as we're heating from the outside in. As our vessels increase in size, it becomes increasingly more difficult to control our reaction temperature precisely, especially if we have very high exotherms. The larger our reactor becomes, the more difficult it is to control those functions. If we think about mixing in a batch reactor, our mixing is chaotic, it's turbulent. It's not the same in every process. We can increase mixing efficiencies by using multiple propellers. We can have baffled reactors to increase that mixing efficiency, but it's still chaotic, it's still turbulent. If we think about addition, even with controlled dropwise addition, we create concentration gradients. We have more of our reactants in one place over the next. And as we're adding more of our reagents, we can create back mixing as well. So our product can react further. So we create concentration gradients. Molar ratios come into the control of addition. Concentration isn't so much of a factor, but reaction time can be difficult to control precisely, and we can control that under flow reaction conditions. So let's think about some of these parameters in a flow sense. So let's think about mixing initially. So we can create that same turbulent, chaotic mixing under flow conditions with the use of simple static mixers. And there's an example here of a split and recombine micro reactor, a chemically etched glass reactor, where we're splitting each of those reagent additions into three sets, and in a three-dimensional matrix, we're splitting and recombining and splitting and recombining. And we can create very efficient mixing profiles for reactions that require high mass transfer. But under most flow chemistry experiments, we're going to be operating under laminar flow. Now you can see from the diagram here, we don't initially mix our reagents. Mixing occurs in laminar flow under diffusive mixing. So as our reagents meet, they will diffuse into one another, radial and actually. But that diffusion time is proportional to the distance squared, so it's quite quick. But the take-home message here is that it's reproducible. Every mole of our reagents that mix will see, that combine will see exactly the same mixing regime. And as we're moving our reagents on, there's no opportunity for our product to react further with the addition of our reactants. There's no back mixing. So it's fast and reproducible. And that can create quite a lot of benefits. I mean, if I run an experiment with exactly the same conditions and the same concentrations today, I can reproduce that tomorrow, next week, or in a year's time, and I'll have exactly the same reaction conditions. Let's think about temperature. So flow reactors have a high surface area to volume ratio compared with their equivalent batch reactor. That better heat transfer, if I have a high surface area, I can add energy into my reaction and I can also dissipate it very effectively. That high heat transfer gives us better temperature control. If we think about, as I said earlier, heating a batch reactor, the little diagram here shows you that temperature gradient as we're increasing our reaction temperature up to the desired temperature, and even when we take that heat away, there's a temperature gradient as we cool. Because we can add energy in very effectively, reaction temperature, as soon as our reaction enters that heated environment or cooled, inversely, the same thing happens when we cool, it immediately gets to, or very, very quickly gets to the reaction temperature. And when it exits the reactor, that temperature gradient as it cools down is very fast as well. So for those that haven't seen a flow reactor, I'm just going to pause this a second so you can see this in a bit more detail. So what I have here is a simple glass etched microreactor. So this is 1 milliliter in size. Now the equivalent surface area to this reactor is about 80-fold smaller. If we look at a larger capillary reactor, so if we want to scale up, this would be an example of a PTFE tubing wrapped around a heat control element. So this is a larger volume. This is 16 milliliters. And if we really want to go to larger scales, we can use something like this, which is a glass flow reactor, or sorry, a glass capillary, and this one's 250 milliliters. But that surface area to volume ratio is still much greater than the equivalent volume of a batch reactor, and we can control, we can flow continuously through this to create more material with the equivalent volume. So let's take that concept again a bit further. So if we're thinking about selectivities with temperature, so a homogeneous temperature will probably give us better selectivity. We'll be able to control selective pathways if our reactions are thermodynamically controlled. So I've got a little diagram here, which is a simple potential energy against the reaction coordinate graph. We're starting with reaction A, and we're generating a raw temperature range under our batch conditions. Now, this could possibly give rise to byproducts, secondary reactions that are unwanted. If we use a flow reactor, because we've got a high surface area and we can control that temperature distribution in a lot more detail, we can use that to our advantage to selectively choose our reaction pathways by having discrete reaction control. Okay, so that's some of the benefits of mixing and temperature on selectivity. I said that we can achieve faster reactions. So flow reactors have small volumes, so therefore they can be pressurized more easily. You know, I've shown you a 1 milliliter reactor here. If we can achieve higher pressures, then we can achieve higher temperatures. If we can achieve higher temperatures, that generally results in faster reactions if we have thermodynamic control. So if we think about a batch reactor, what are we limited to with our upper temperature, or the maximum temperature that we can operate at? We're limited at that reflux temperature, and it's not just the solvent, it's every element, every component in our reaction mixture. So we can only really get to the boiling point of our lowest boiling point reagent or reactant. Because we can pressurize a system under flow conditions, we can achieve, or we can run reactions under pressurized environments and take them way above their reflux temperatures. If we were to do that under batch conditions, we'd need specialist apparatus. We'd need a bomb, a stainless steel vessel. Now, these are restrictive when we start to scale up. Because of the continuous nature, we can take chemistry that we would generally operate on a fixed volume in a bomb and scale that up. Just to illustrate the point here of how we can speed these reactions up, we've got a little table here with a few solvents and their boiling points. And just to illustrate, by applying pressure to the system, we can increase the boiling point and maintain our reactions in a liquid state. We all know that water at 1 atmosphere boils at 100 degrees. We can typically take our flow reactors up to 20 bar. So we can take water well above 200 degrees. Now I've got DCM in there. I mean, this is a solvent. We can potentially take DCM 4 times higher than its boiling point. You would generally, I mean, I can't think of an application where you'd want to take DCM to 160 degrees, but that's just to illustrate we need to consider the boiling points, vapor pressure of all of our components within a reaction mixture. So if you think back to your physical chemistry days, this is the Arrhenius equation. I'm not going to go into the dynamics of this equation, but essentially what it says that with every 10 degrees increase in reaction temperature, we double our reaction rates or half our reaction times. So potentially, if we could increase the temperature of our reaction by 100 degrees, we can vastly accelerate our reaction times. And this is a really nice benefit for process of intensification, for taking reactions that may take hours down to tens of minutes to seconds. So there's a really strong benefit for being able to pressurize and run pressurized reactions at elevated temperatures. So how can we achieve safer reactions under flow? How can we reduce the associated hazards with our chemistry? Now, the first point that I make here is that we're always reacting a smaller quantity of material at any point. Now, this 1 milliliter flow reactor, I can continually pump through liters of material, but I'm restricting the amount of reactions that's occurring to that 1 milliliter scale. As I said, we've got a higher surface area to volume ratio, so we can potentially control extremely exothermic reactions and keep it to within a small temperature window. I've run neat nitrations that generate, you know, tens of watts of energy and maintain those within a couple of degrees of the set temperature. We can make things like reactive intermediates and hazardous reagents in situ. This means that we don't have to have big feedstocks of those restricted reagents. We can create very highly energetic intermediates in situ and react them on further without any isolation or workup. And we can also, we spoke about pressurizing reactors to increase the reaction temperature, but we can also use that pressure in the system to carry out chemistry that evolves gas. You know, we all know that the definition of a reaction that involves gas very quickly is a bomb. Now, because we're reacting a small amount of material at any point, we can control the evolution of gas. And because we're applying a pressure to the system, a back pressure, we can help maintain or help keep that evolved gas in solution. Now, a simple analogy to show how we can reduce that hazard potential is that if we have a 10-liter batch reactor and it explodes, we have a reaction that runs away, we've got some serious consequences. But I can pass that same 10 liters through a 10 milliliter reactor, ensuring that we're only reacting a small volume at any point. Now, if that reaction's fast, this will only take a short amount of time. I can leave that running and process that material all day or overnight. So we greatly reduce the associated hazards with our chemistry. So the next point I made at the beginning was, how can we achieve reaction optimization more efficiently? So in a flow reactor, it's very easy to vary our continuous variables. So things like reaction time, we can vary the reaction time by just varying the flow rate for our fixed volume flow reactor. We can vary the reaction temperature very quickly because we have a low thermal mass with a much smaller reactor. We can vary the reagents or the ratio of reagents, those molar ratios, if we have a known concentration, simply by varying the flow rate of the addition of those reactants, we can control the stoichiometry extremely precisely as well. We can vary the concentration by varying solvent streams. So they're discontinuous variables. We can easily automate our flow process to explore all of those parameters. But we can also look at discontinuous parameters, things like reagent screening. So by using, I've just put up a little picture here. This is a simple liquid handler. Now, lots of them on the market that allow us to aspirate from different vials and inject into our flowing stream a range of reactants. So we can do reagent screening, catalyst screening, enzyme screening, etc. So we can look at those discontinuous variables as well. If we think about doing reaction optimization in batch, what we'd do typically is we'd set up discrete individual reactions exploring the varied reaction conditions we want to explore. In a flow system, because we can flow a plug of material, a small aliquot of material into our flowing stream, it means that that's separated and isolated by the solvent that's pushing that slug through, which means that we don't need multiple vials. We only need one reactor because our reactor is flushed out. And if we automate that process, we can have multiple slugs flowing through our system and explore that whole range of reaction parameters. So it means that we can look at tens to hundreds of reaction conditions with very minimal setup. All we need to do is create our initial reagent or reactant solutions. And we can do all of this in an automated fashion. So if we take that principle of being able to add different reagents into our flowing stream, look at discontinuous variables, we can expand that and look at library synthesis. So if we think about how we do library synthesis in classical methods. One of the key requirements for doing this, especially in the pharmaceutical industry, is the need for an increased delivery of novel structures, novel diverse chemical compounds to explore our therapeutic area projects. Now, we need that to feed in high throughput screens. Still the best method for generating new lead structures, but the hit rate's low. When we typically carry out array or library synthesis under classical methods, this often delivers low yielding and unreliable reactions that require reoptimization and resynthesis when we scale up. And we also have time-consuming purification steps in between each of those steps along the path of building our final compound. So this greatly slows down that whole process. If we think about using flow methodology to create libraries, we can use all of this enabling technology to explore vast arrays of novel, diverse compounds. So we can automate this process and have walk-away multi-step reactions. And we can harness all of the benefits that we're talking about to have better control and deliver better chemical processes. So we have increased value in our synthesis. And we can start to look at reactions that we may have avoided due to safety concerns. Some of those restrictive chemistries we can now perform conveniently under flow chemistry conditions. The point here is also that I wanted to emphasize is that for many of our library sets, if we have a hit, the resynthesis and scale up is already done for us. All we need to do is take those initial reaction conditions, put them back into our flow system, and just flow more material through our flow system to create more of that targeted compounds that we've identified. So that brings me neatly onto why scale up is easier under flow. Now, I think this should be quite apparent. It's a continuous process. For those kind of lab scales, when we want a 10 or 100-fold scale up, it's just possible to run for longer. I always use the analogy of filling a cup from a tap. You know, if we leave a tap running, I can fill a cup. If I leave that flowing longer, I can fill the bath. And get it in the right temperature is our optimization. Once we've found those conditions, we can just flow for as long as we like, as long as we have the feedstocks and the collection vessels to collect everything. If we want to scale up even further into kind of pilot and manufacturing type scales, the fundamental principles of flow chemistry still hold true. Now, I showed you one of those big 250 milliliter flow reactors. From that, the throughput that I can get will take me into the kilograms or multi-kilogram per hour kind of avenues. And we can still do that safely and efficiently. When we go to larger scales, we need to understand our chemical engineering in a bit more detail. We need to understand heat and mass transfer and the associated methods for controlling those. It's a slightly different technology from a lab scale. So when we're talking about throughput on a lab scale, typically we're looking at milligrams to tens or hundreds of grams of material per hour. You know, if we have a fast residence time, a fast reaction rate, I'm going to be able to generate more material. If I have higher concentrations, I can generate more material per unit time. On a pilot and manufacturing scale, as I said, we're talking of kilograms or multiple kilograms. And that saves us time and money in scaling up these types of reactions. So we can also integrate reaction analysis into a flowing stream. Now, if we think about running multiple reactions under batch conditions, simply, if we're using a method like LC or mass spec, we need to take a sample. We need to take a sample and dilute that from every single reaction that we're carrying out. Excuse me. If we're using a technique such as IR, we need multiple probes. Now, in flow, because our reaction is mobile and we're using one reactor typically, we only need the one probe. So if we're looking at reaction analysis, the techniques that we can use, for continuous non-destructive analysis of things like IR, Raman, UV, and even continuous NMR. Although these machines are generally have low resolution. They don't give us the detail that we require, but they're very good for looking at diagnostic peaks. We can also use destructive methods such as LC and mass spec. With continuous analysis, we can place our probe anywhere in our reaction stream. If we're doing multi-step synthesis, we can look at our intermediates as well as our products forming. For methods such as LC and mass spec, we need to take a sample from our flowing stream, divert that, dilute it typically to get better resolution in these techniques, and then send it to that analytical device. So we can continuously monitor the progression of our reactions. We can use this, if we're scaling it up as well, to monitor the reaction profile over a period of time to see if that decreases or changes. So I have a few little pictures here just to give you an idea of the size of these analytical devices that we can use in the flow stream. So the first one there is a little benchtop NMR. You can see the size of that by the screen behind it. These are typically low resolution, as I said, 50 and 60 megahertz, but they're very efficient for looking at diagnostic peaks. The next instrument there is a flow IR cell. This one's from Metna Toledo. This doesn't need any cryogenics. We can just flow into the cuvette and flow out again. So we can look at continuous IR. And the last instrument there is a sample and diluter. All that allows us to do is take an aliquot from our flowing stream, dilute it, and pass it on to another device. So I've said that we can also do reaction workup continuously, as well as making our compounds. So under batch conditions, workup generally relies on separate operations. It's a discrete function, whether we are doing an aqueous workup, a liquid extraction, whether it's a filtration, or we're using solid phase scavengers to take out one of our components. Now we can do that under flow conditions as well. Because our reaction is already mobile, it's easy to implement techniques that allow us to work up continuously as well. So we can use things like continuous liquid-liquid extraction. So we can have a continuous separating funnel, or we can use things like solid phase scavengers. Typically with scavengers, what we do is take a glass column and fill that with some kind of scavenging or sequestering supported reagent. Now the easiest one to illustrate this technique is something like an SCX column. If we have a column packed with that kind of media, whether it's an amylist or it's a polystyrene beads, that sulfonic acid group will take out excess amine. And there are lots and lots of examples where we can use column reactors filled with sequestering reagents to take out multiple components, unwanted excess reagents from our reaction mixtures. So I just want to take a little a small amount of time just to talk about phase separators. So a phase separator is essentially a continuous liquid extractor. There are many of these on the market. But what we need to do is we need to extract our material into our flowing stream with a secondary extraction solvent. We need some kind of separator to separate the two flowing streams. So what I've got here, and I can get in a bit closer, is a membrane separator. So this is a small scale one. So what this device is internally in here we have two glass plates that are separated by a hydrophobic membrane. Now that hydrophobic membrane allows us, in theory, if we have a mixture of organic and aqueous media, as we would have in a liquid-liquid extraction, to repel the aqueous, and if we have the right cross-membrane pressure, pass our organic through. Now the first diagram I've got here is just showing that extraction process. We have our reaction mixture and our extraction solvent meeting at a T-piece, and then we can create very small liquid-liquid partitions. We can create a very high surface area where our extraction takes place. Now that's typically in a length of tubing. Now once our extraction is carried out, we flow that into our membrane separator, And this just illustrates the point I was making earlier, that hydrophobic membrane will repel the aqueous phase. And if we have the right cross-membrane pressure, a positive displacement from one side to the other, we can push our organic free. Now, we can put a device like this anywhere in a multi-step synthesis. So not only can we use this to work up our reaction at the end of the process, we could put it after an intermediate, for an intermediate workup, for example. So this offers us lots of benefits. Now, before I go on to some of the chemistry examples, these are the types of questions that I generally ask people when they're considering using a flow chemistry technique. So, do you have a scale limit? Does your risk assessment restrict you from using certain materials? Do you have the glassware? You know, if you want to make 10 liters of material, do you physically have the glassware to make that in one go, or are you going to need separate reactions in batches to make that material? Do you have a temperature limit? Does any of your calorimetry data say that you have an exotherm that's very difficult to control? We can use that heat dissipation effect of having a high surface area to volume of controlling those types of reactions. Do you need a low temperature? Have you optimized your chemistry under a microwave condition? You know, it's very difficult to scale up microwave chemistry. We can do that very effectively under flow conditions. Do you need controlled additions? Do you need to control your stoichiometry precisely? You know, if you're having problems with addition and mixing, do you generate reactive intermediates or hazardous byproducts? We can control all of those. So all of these are safety issues, really. If the answer is yes to any of these questions, then design a flow chemistry experiment would possibly give you some benefits. So I'm going to spend the next period of time that we have, and I'm overrunning a little bit. If you be patient with me, I can illustrate some points. So these aren't the most groundbreaking chemistries. I could have chosen from hundreds of flow chemistry examples in the literature, but these are nice examples that illustrate some of the points that we're making. So I'll start off with a simple thiazole synthesis. This is a one-step process. What this is showing is that we can, by using these enabling technologies, we can optimize our reaction conditions very quickly and efficiently. All I need to do here is make up my reagent concentrations, and then I can explore a number of parameters. So here I'm looking at time, temperature, and water equivalence. So very minimal setup. I've explored 9 reactions here in just over half an hour to get to my desired, to my optimized reaction conditions, which then I can then take back a step and flow for longer and create more material. So very efficient at getting developing reaction methodology and then being able to scale up. This next example takes that idea of temperature control for reaction pathways and just illustrates it in a bit more detail. So this is a nitration of a pyrazole done at AZ a few years back. Their calorimetry data identified a very strong exotherm that was leading to their dinitrated product. Now, if you look at that reaction scheme there, the temperature difference between the mono and the di material is only 15 degrees. Now, with very exothermic reactions such as nitrations, I think you all agree that controlling reaction conditions to within 15 degrees is quite difficult. If we look at the temperature distribution profile here, by having a very, very precise control of our reaction temperature, we can get to the mono selectively over the dinitrated product. And no one wants lots of nitro groups in their compounds. So this illustrates temperature control over selectivity. So this next example here is showing quite a few benefits. Now, I wouldn't worry too much about the fluidic diagram here. It's more the chemistry and what it's offering. So this is taking chemistry that is probably quite difficult. Well, we know is quite difficult to do under traditional batch methods. So we're taking an ester and we're selectively reducing it to an aldehyde. Now, typically, the way we do that under batch conditions, because it's difficult to control over reduction, is we take our compound down to the alcohol, reduce it down to the alcohol, and then oxidize it back up to the aldehyde. Now here, because we can control the stoichiometric ratio of the DIBAL that we're using here in as our reductants, we can limit over-reduction. What we're also doing to limit that over-reduction is we're quenching in situ as well. So in this example, as we would do under batch conditions, we call our reaction typically to have controlled temperature control over these types of exothermic reactions. So the first step in this reaction is done at low temperature, and as we would do under batch conditions, we're then allowing that to warm up to room temperature to drive this reaction to completion. So what we're doing is we're cooling our ester and our DIBAL down to our reaction temperature, -70, and we're reacting that through run reactor to perform that reduction. Now, to limit over-reduction, we're adding in methanol as a quenching reagent, and we're pre-cooling that before we're mixing as well. So you can see from the output here, we're generating less than 1% of the over-reduced material. So what we're doing here is we're controlling reaction temperature, we're controlling stoichiometric ratios, and we're increasing selectivity to the compounds that we want. Now, we've spoken about using continuous workup in our reactions. So this example here shows a multi-step synthesis, which is one of the other benefits that we haven't spoken about here, but we will do in future. So we're using inline phase separators at the end of the process here to work up our final reagent, but we're also using it as an acidic quench. So we don't need to use it to extract anything. We're using it now to protonate the intermediate that we're forming from this Grignard reaction. Here we're forming a Grignard in situ, so we're making a reactive intermediate in situ. We're reacting that on further with our aldehyde. We're doing in situ quenching, and a protonation, and then we're reacting with our nucleophile onto our final product. So this is using identifying a number of benefits in our reaction over traditional batch methodologies. And this is a 1, 2, 3, 4, 5 step synthesis with no discrete workup steps. The next example illustrates reaction selectivity on a material. So this is making calcium carbonate simply from calcium chloride and sodium chloride. Now, we're using exactly the same reaction conditions, concentration, temperature, and reaction time. But you can see with those SEM images of the batch and the flow process, and the batch conditions, we have things like temperature and concentration gradients. So we're losing control of the particles that we're making under flow conditions because we have that exquisite reproducibility in mixing and temperature control. You can see that the particles we make are uniform. So this is a really nice example, visual example of showing selectivity under flow conditions. So the next example I'm going to show is creating hazardous intermediates. And I've noticed that I've got a slide missing from my deck here. But what I want to do is just take another poll from you guys. And that poll is, when was the last time you used diazomethane? And that's probably going to give away the example. So if you just take a few minutes just to fill that poll in, if you've never used diazomethane, I don't blame you, because it's a horrible reagent. But what if we could use diazomethane, generate diazomethane in situ and use it safely? So I think the polls are coming in.
Well, nearly there. Just a few more people. I have some brave people and stuff.
Okay, some brave people. Some of you use diazomethane regularly, and you still have all your fingers, hopefully.
Nearly everyone.
Okay, so what is this looking like, Ryan? Excuse me. Okay, I have no fear. Okay, so most of you have used it occasionally. So let's just explain what I was going to talk about. So in this example, we're going to be talking about creating hazardous reagents in situ, and diazomethane is probably the most extreme example of that. I like using this example because it's really nice. It's difficult chemistry. So this derives from the needs from the chemists in this example, needing to look at a diverse range of HIV protease inhibitors. But if you look at the core of this chemistry, it's an alpha haloketone, which is common to all of these diverse biological active materials. So how would we generate that alpha halo ketone under traditional methods? So I think the most direct route would be this. You know, we take our amino acids, we react with an acid chloride to make our mixed anhydrides, then we'd react that on further, condense that to form the diazoketone, and then we do a simple hydrohalogenation to get to our alpha haloketone. Now, the elephant here in the room is diazomethane. Now, diazomethane is arguably a very green reagent. You know, one of the only byproducts from this reaction is nitrogen, but it's explosive, it's shock sensitive, it's extremely toxic. When we want to use this reagent normally under batch conditions, we need flame dried glassware, no ground glass joints, nothing that could create any static, or it's a difficult reagent to use. But what if we could generate that in situ and use it safely? So this is what the chemists set out to do. So what we're doing here is we're using a technique that Steve Lay from Cambridge University developed a number of years ago, and that's using the tube-in-tube reactor. So now diazomethane is a gas, and here we're generating diazomethane in situ. It's permeating through that gas permeable membrane that runs through the center of our tube-in-tube reactor, and it's been able to saturate our flowing reagent stream. Here this is THF. So what we're doing is we're taking an air-stable reagent, Thiazole, the diazomethane precursor. When we react this with base, we generate diazomethane. As I said, this permeates through the inner membrane tubing, and we're able to saturate the flowing stream. So what we're doing here is, like most chemistry, we need to optimize certain reaction steps. So here we're taking a stream of THF, we're saturating it with diazomethane, and then we're quenching that with a simple carboxylic acid to methylate that, so we can work out how much diazomethane we're generating and work out the yield to take on to further steps. But what we're also doing here, not only are we using a small volume reactor, so we're only generating about 2 milliliters of diazomethane at any point, is the output of that reactor is being immediately quenched, not only with the acidic reagent, but the output is going to a acetic acid waste pot, and we're destroying any excess diazomethane that we're generating. So we're making it, we're using it, and we're destroying it. So it's a very nice, safe, efficient way of handling this reagent, or generating this reagent. So what we can do then is we can telescope that whole process. So here we're taking our amino acid and our acid chloride, reacting through RT1, our first flow reactor, to generate our mixed anhydrides. We're condensing this with the diazomethane, and then we're adding a third stream. Here we've just got hydrochloric acid solution to do that hydrohalogenation to get to our desired compound. Now, this is generated over 3 steps with no workup, and we have an 87% yield, which is extremely good. But we're allowing the direct formation of a very hazardous reagent, without the need of having a larger amount as a feedstock. So the last example I'm going to show here, and I know that I can see that I'm running out of time, so I'll go through this one quickly. This is just showing how we can use multi-step syntheses or multi-step telescoped reactions under flow conditions to give us a wide range of diverse compounds. So we spoke about some library synthesis, so this is an example of doing that. So this is a library where we're looking at oxadiazoles. So the typical way you do that under batch conditions is take your amidoxime and your acid, use some kind of coupling reagent, apply some heat to do the cyclization. But we can take back each of those reagents, or reactants, the acid and the amidoxime, back to their starting materials. And we can use liquid handlers to increase the diversity In this instance, we have the aryl and heteroaromatic nitriles and this aminopyridine to make the imidazole pyridine precursor. So like any chemistry, I said we need to optimize our conditions. I've already said that we can do this very quickly and efficiently. This is just taking standard coupling methodology and varying reaction temperature to get from our coupled material to our cyclized material. Now, what if we wanted to increase the diversity of the amidoxime that we're using? We can take that back a bit further and use that aryl nitrile and hydroxylamine, a bit of base, to make our amidoxime in situ. Now, we'll take the amidoxime monomer set that we're making, and we can use those optimized conditions for coupling to react on further to our oxadiazole. We can also take that step back again from our other monomer, our acid. And here, if we use a range of aminopyridines, we can get to that imidazole pyridine carboxylic acid precursor. And now we've got a 3-step synthesis. We're making a diverse array of each of our building blocks, and we're coupling to get to our end products. Now, I said we could take maybe from this library array, one of those compounds or a couple of them may be a hit. So we'd need to work them up. So the last slide here is just showing that. I'm not going to go into too much detail here. This webinar will be available for you guys to look back over later, or you can just drop me a line and I can give you the references for these illustrations that we're talking about. But now, what we're doing, instead of just flowing for longer to create more material, we're increasing the reactor, our flow reactor volume, so we can flow faster to create more material. And in these 2 steps here, we're also adding some phase separation. So in here we're using DMA in the coupling reaction, which is a high boiling solvent. We can extract that out, just get rid of that, and makes our work up a little bit easier. So this is showing that we can create diverse subsets. We can harness that telescope process and have in situ workup as well. So I wanted to leave it there. Hopefully we've covered some of those key benefits, and I'll pull these up here. I'm not going to go through them all for time. Hopefully I've set out to what I promised to do at the beginning of this webinar. Hopefully you've learned something, and I'm hoping that some of you have asked some questions along the way. So in the remaining time that I have, and I know that I've overrun with your time, so we'll keep it brief. I'll take a few questions and then I will reply to all of you and answer your questions as soon as I can. So for me tomorrow. So first one.
Okay, first question. Does the performance of the continuous solid phase extractor drop during a run? How is the solid phase regenerated?
Okay, so that's a question about using solid phase reactors. Does the performance drop, and how are they regenerated? So that's one of the limitations of using a column reactor or a packed bed reactor, is that it has a finite amount of material in. Whether that's a supported reagent or it's filled with a solid reagent, there is only a set amount of material that we can operate. That we can use, a certain amount of reagent. They will deplete. Now, to regenerate those, there are examples where we have multiple columns in parallel. When one's depleted, we can switch to use the second column while we're regenerating the next. Now, if we have a simple ion exchange resin, by simply flowing through with a salt solution, that's anion can then reattach, and we can use that reagent again. If we're using a solid, now that will be depleted. Now, the performance of using supported reagents is probably better than solids. With solids, we can create channels and fines, which restricts our control over the distribution of our substrate as it flows over the column. So hopefully that helps.
Can you explain how you might perform electrochemistry in continuous flow?
Okay, so there's a question about running using electrochemical methodologies or continuous electrochemistry. That's a really good question, actually. Electrochemistry is often a technique that's very underutilized, analogous to photochemistry. Here we're using electrons as the reagents. The hurdle for doing this is most people haven't run an electrochemical experiment since their undergraduate studies. The problems of using electrochemistry when we're running it, doing it under batch conditions, that we generally have a big space between our electrodes, and that can lead to, we spoke about temperature and concentration gradients, this can lead to electron gradients as well. What we do when we're using continuous electrochemistry techniques is we bring the distance between those electrodes down so they're very close. So we have precise control over the number of electrons that are passing into our flowing stream. If we can do that, then that can help us be more selective in our oxidation. Our electrochemistry is oxidation and reductive techniques. We can change the nature of the electrodes very efficiently. As I say, we can control the gap in between them. And because we have a small distance between the electrodes, it often leads to us needing less electrolyte as well. I would say with using electrochemistry in a continuous process is probably greener as well, because we're eliminating the need of heavy metal oxidants, which are toxic and require disposal, and those pyrophoric reductants that we generally use.
Another question, how do you manage to perform reactions under inert conditions?
Okay, someone has asked, how are we able to perform reactions under inert conditions? Well, that example that we showed earlier, that DIBAL reduction from the ester to the aldehyde is done under anhydrous dry conditions. We have a semi-closed flowing system. What we can do is just pass a dry solvent, an anhydrous solvent, typically methanol to begin with, through our reaction fluidic network. Methanol is really good for taking out dissolved water or residual water, and then we'll flow with an anhydrous reaction solvent. Now, if we keep our starter materials under inert condition, under a nitrogen or a argon blanket, for example, we can keep that whole system dry, and that limits the problems with hydrolysis products of things like, you know, lithium and magnesium salts. Got time for one more? Got one more in there?
Yes. Last question we can answer now. If I would like to use a catalyst for my reaction, how would I be sure it's completely interacting with the reagents? And how will I recover it from the mixture?
Okay, so a question about, was worded, if I want to use catalysts in my reaction, how can I be confident that
it's completely interacting with the reagents?
Okay, it's completely interacting with the reagents and that I can recover it. It depends if you're using a homogeneous or a heterogeneous catalyst. There are more heterogeneous catalysts than homogeneous catalysts. We can use heterogeneous catalysts in columns. If we're packing a fixed bed reactor, a column reactor, with a homogeneous catalyst, we generally have more catalyst to substrates. So we can increase the turnover. We can often increase reaction rates. And because it's fixed and it's heterogeneous, we can recover that by simply drying out the catalyst and extracting it from the column. If we're using homogeneous catalysts, those being in solution, then they will mix and react as they would do in any batch reactor. You know, we were talking about more efficient mixing and less back mixing. We may need slightly more catalyst because we're continuously flowing that through the system. But recovery would be, so the end process of a flow reaction, as I said right at the very beginning, this is just a synthetic technique. We can use workup techniques, but we still need to work up and isolate and treat our collected end material as we would do in any other chemical reaction. So we'd isolate that as we would do normally. Okay, so thank you for your time, guys. I know that I've overrun. Hopefully this has been useful. I will get back to all of the other questions as soon as I can. So this is, as I said, the second in a series of webinars that we're giving. The next one will be on techniques of converting your batch chemistry conditions to flow chemistry conditions, tips and tricks, and then we'll go into more detailed applications in further webinars. Now, There is a feedback survey that will appear after I finish this session. If you can take some time to fill that in, that would be fantastic, because it helps us make these webinars better. So tell me what you like and what you don't like. So again, thanks for your time, everyone, and I'll see you next time. Thanks.